Welcome to Mythosium, where we make sense of the strange, explore the misunderstood, and explain the science behind the myths you've always wondered about. Today we're investigating a classic urban legend, one that's been repeated for decades. If you dropped a penny from the top of a skyscraper, could it kill someone below? It sounds dramatic, a tiny coin falling thousands of feet, turning into a deadly projectile as it picks up speed. But does physics really work that way? Let's find out. First, let's look at the myth itself. The idea goes something like this. A penny, though small, could accelerate to incredible speeds when dropped from a tall building, fast enough to strike a person on the ground and kill them instantly. At first, this seems plausible. A penny has mass. Gravity pulls it downward, and falling from great height should mean huge speed and enormous impact, right? But that's not how the real world works. The key factor that this myth ignores is air resistance. Let's start with some numbers. A penny weighs about 2.5 grams, roughly 1/10 the weight of a small marble or about half a bullet. If you were to drop it in a vacuum, where there's no air resistance, it would accelerate due to gravity alone, 9.8 meters per second squared. From the top of the Empire State Building, which stands about 443 meters tall, the penny would reach a speed of over 300 kilometers per h before hitting the ground. That's roughly half the speed of a typical handgun bullet. If that were true, the impact would indeed be devastating. But we don't live in a vacuum. The Earth's atmosphere changes everything. As the penny falls, it pushes against the air molecules below it. The faster it goes, the greater that upward push becomes. Eventually, the downward force of gravity and the upward force of air resistance balance out. When that happens, the penny stops accelerating. It falls at a constant speed. This is called terminal velocity. Every object falling through air has a terminal velocity. It's determined by the object's weight, its size, and its shape. For a penny, that terminal velocity is around 80 kilometers per h, or about 50 miles per h. That's fast enough to sting, maybe leave a bruise, but nowhere near enough to kill. You can see this effect all around you. If you drop a feather and a hammer on Earth, the hammer falls faster because air pushes harder on the feather relative to its weight. But on the moon, where there's no air, both fall at the same rate. Astronaut David Scott demonstrated this in 1971, dropping a hammer and a feather on the lunar surface. They hit the ground together. That's because in a vacuum, air resistance doesn't exist. But on Earth, air resistance dominates. That's why a falling penny slows down and stabilizes, floating to the ground at its modest terminal velocity. To experience this firsthand, think of skydiving. A person in free fall quickly stops accelerating and begins falling steadily at about 200 kilometers per h, their terminal velocity. That speed depends on body position and air density. When skydivers spread out their limbs, they increase drag and slow down. When they dive head first, they reduce drag and go faster. It's the same principle for a penny. Its small mass and large flat surface create a lot of drag relative to its weight. That's why it reaches terminal velocity after falling just 15 or 20 meters, and won't fall any faster, no matter how high you drop it from. Even if you dropped it from orbit, it would quickly hit its speed limit as soon as it entered the atmosphere. So, no. A penny from a skyscraper won't kill you. It might smart a little if it hit bare skin, but it's far from deadly. But that leads to another question. If pennies are dangerous, what falling objects are? To answer that, let's look more closely at terminal velocity and air drag. Air resistance increases with speed, specifically with the square of speed. Double the velocity, and air resistance quadruples. It's also affected by an object's shape. Smooth aerodynamic shapes slice through air easily. Irregular or flat shapes generate turbulence, creating drag that slows them down. This relationship is captured by a number called the drag coefficient, a measure of how streamlined an object is. A perfect sphere has a drag coefficient of about 0.5. A bullet, depending on its shape, can have a drag coefficient as low as 0.1. That's why bullets are designed to fly straight and fast, while coins tumble and flutter. A penny's shape is terrible for cutting through air. It's flat, light, and unstable. It tends to wobble as it falls, exposing more surface area and increasing drag even more. This tumbling motion also means the penny doesn't have just one terminal velocity, it has two. One when it's flat, and one when it's edge-on. It constantly flips between them, oscillating as it falls, so not only does it fall slowly, it falls unpredictably. Now let's compare it to other falling objects. Take raindrops. Raindrops typically fall at around 25 kilometers per h-hour, slow enough that they don't hurt when they hit your skin. Their shape flattens as they fall, increasing drag and limiting their speed. But hailstones, on the other hand, can reach speeds over 200 kilometers per h-hour. That's because they're larger and heavier. Drag increases with the square of the radius, but weight increases with the cube. So as hailstones grow, their weight increases faster than their drag, meaning they can fall much faster. That's why large hail can crack car windshields or injure people, and occasionally even cause fatalities. The same principle applies to other objects. A baseball falling through the air could easily reach speeds of 150 to 200 kilometers per h-hour, delivering over 80 joules of energy on impact, more than enough to fracture a human skull. Even small tools like a wrench or a hammer, if dropped from a height, can be deadly. Every year, hundreds of people are seriously injured or killed by falling construction materials, not because of their height, but because of their mass and shape. But what about something more streamlined, like a ballpoint pen? A pen is heavier than a penny, and thinner. That means less air resistance relative to its weight, and therefore a higher terminal velocity. Could that make it dangerous? In theory, a metal pen with its cap removed could hit the ground at several hundred kilometers per h-hour if it fell point first and stayed stable. But that's unlikely. Like the penny, it tumbles and wobbles, which increases drag and slows it down. So while it might leave a mark or bruise, it's not going to be lethal. The only objects that fall fast enough to be deadly are those that are both heavy and aerodynamic, things that maintain a stable, streamlined shape as they fall. During World War I, early pilots dropped small metal darts called flechettes, designed to fall point first, piercing helmets and even armor. These darts were simple kinetic weapons, relying purely on gravity and their shape to reach high terminal velocities. Their weight, combined with their small surface area and pointed ends, made them extremely efficient at cutting through air. Even without explosives, they were deadly. So why don't bullets behave the same way when dropped? Because they tumble too. A bullet fired from a gun spins rapidly due to grooves in the barrel called rifling. That spin stabilizes it, keeping it point forward. But when dropped from a height, it doesn't spin. It quickly flips onto its side, maximizing drag and slowing down dramatically. So a bullet dropped from a building wouldn't be much more dangerous than a penny. But a bullet fired upward into the air is another story. If it's not perfectly vertical, it retains some horizontal velocity and spin as it falls, making it stable and deadly when it comes back down. That's why celebratory gunfire can kill people miles away. So now we can summarize what truly determines whether a falling object is dangerous. Mass. Heavier objects carry more momentum and energy. Shape. Streamlined shapes fall faster, flat or irregular ones fall slower. Air density. At higher altitudes, thinner air means less drag, allowing faster speeds. Terminal velocity. The balance point between gravity and drag determines maximum speed. To cause fatal injury, an object typically needs to deliver around 68 joules of kinetic energy, the amount required to fracture a human skull. A penny at 80 kilometers per h-hour delivers about 0.2 joules. A baseball, over 80 joules. A heavy wrench, even more. That's a difference of hundreds of times in impact energy. So the verdict? The myth is busted. A penny dropped from the Empire State Building won't kill you. It won't even break the skin. It might sting, sure, but that's about it. What it will do, however, is teach us something fascinating about the physics of falling. How air resistance, shape, and mass interact to limit the speed of every object around us. From raindrops to skydivers, hailstones to bullets, everything that falls through Earth's atmosphere is shaped by the same balance between gravity and drag. And that's what science does best. It takes an old story, tests it, and reveals the simple, elegant truth behind it. So the next time someone tells you a penny could kill you from a skyscraper, you'll know better. You'll know that physics, not fear, decides what's truly dangerous. Thanks for watching. If you enjoy learning how myths meet science, make sure to subscribe to Mythosium, where we make the invisible laws of the universe simple, surprising, and real. Because understanding the world doesn't make it less mysterious. It makes it more amazing.